Hello everyone, so in this video I'm going to go over section 2.3, the chain rule and trigonometric derivatives. Really there's just another set of rules that you have to remember for this section, and I'll just go ahead and show you the rule, do some practice problems, and that's essentially how you get good with derivatives. So the chain rule is kind of an extension of the power rule. Essentially what you have to do is if you want to take the derivative of some sort of like polynomial function, right? So let's say we have f of x and the whole polynomial function is raised to a power of n. What that's going to be equal to, it's very similar to the power rule where we get the n, bring it up to the front, multiply it by whatever you had for the function of f of x, subtract 1 from the exponent, but this time you're going to have the added step of multiplying by the derivative of whatever's on the inside. So it's going to be times the derivative of that function inside the parentheses. All right. And really, if you think about it, you kind of already are doing the chain rule if you did something like x to the third power, for example, right? Because again, what I'm doing is I'm getting the 3, bringing it to the front, subtracting 1 from the exponent, and then what I'm essentially doing is multiplying by the derivative of whatever's on the inside, but the derivative of x is just 1. So, like I said, it's pretty much an extension of what we learned in the power rule, except it's not just going to be x, now you're going to have like a whole polynomial inside of a parentheses. So, let's kind of do the first example. So, if we did part A, well, I want to take the derivative of this function, right? So again, I have an entire polynomial raised to a power. So what I'm going to do to take the derivative of this is I'm going to bring the 4 down to the front, keep everything the same inside, then just subtract 1 from the exponent, and then multiply by the derivative of the inside. So the derivative of the inside is just going to be 3 for 3x, and then minus 0, so we'll just leave it as 3. And so we can kind of like combine the 3 and the 4 together, so that'll be 12 times 3x minus 1 cubed. All right, so again, chain rules, again, just pretty straightforward. You just have to remember to do that extra step of multiplying by whatever's in the derivative of the derivative of the function inside the parentheses. So we'll just do a few more examples just to kind of make sure we understand this. So again, similar with this one, but again, if I don't like working with radicals, I'd rather see the actual exponent. So I'm going to rewrite this as 2w to the 4th plus 5, and then all raised to the 1/3 power, right? So I'm going to go ahead and bring the 1/3 over to the front. So f prime of w is equal to 1/3 times 2w to the 4th plus 5. And then I'm going to subtract 1 from 1/3. So 1/3 minus 3 over 3 is negative 2 over 3. And then times the derivative of the inside. So it's going to be 2w to the 4th. Derivative is going to be 8w cubed. Right? And again, you can. I'm okay if you guys just leave your answer like this if it's a free response. But again, if you were to see this as potentially as a multiple choice answer choice, you could just go ahead and this last term can be combined with that first term, so it'll just be 8w cubed over 3, and then this is being brought down to the bottom, 2w to the 4th plus 5 to the 2/3 power. And again, you might, sometime maybe they'll show the radical, maybe they won't. I won't spend too much time on that. All right. So for part F, another situation, parentheses, function inside, raised to the same power. So what I'm going to do, I'm going to bring the negative 2 up to the front. So f prime of x is equal to negative 2, parentheses, negative x to the 4th minus 3, all raised to the, and then we subtract 1 to the negative 3rd power. Then times the derivative of the inside is going to be 4 or negative 4x cubed. And sometimes it'll be more than one term on this side, but I mean, I guess all of the examples I thought of, well, I guess I could have done B, but whatever. You'll just have one term for this one. So if I combine the first term or the last term in the first term, that'll just be 8x cubed, and then parentheses negative x to the 4th minus 3 to the negative 3rd power. And if you want, you can go ahead and bring this down to the bottom. So it'll be 8x cubed over negative x to the 4th minus 3 cubed. All right. So that's essentially how you do these examples for chain rule. I'm going to move on to trigonometric derivatives. All right. So with the trigonometric derivatives, obviously we should know what our main 6 trig functions are. We have sine, cosine, tangent, and then we have cosecant, secant, and cotangent, right? So if we want to find the derivative of those, it's just a set of rules you got to remember. So if I wanted to take the derivative of sine of, and I'm going to use u for now, okay? I think it'll make it easier to explain some of these. So the derivative of sine of u, it's going to be the cosine of u, and then I'm going to, again, so if they give you the sign of something and tell you to take the derivative, it's going to now be the cosine of that something, but then you always have to multiply it by the derivative of whatever's inside. All right, so if I want to take the derivative of tangent of u, it's just going to be secant squared of u times u prime. All right. And let's keep going. So if if I wanted to take the derivative of cosecant of u, that's going to be equal to negative cosecant of u times cotangent of u, ran out of space, times u prime. Should have started over here. Okay. And then if I took the derivative of secant of u, that's equal to secant of u times tangent of u times u prime. And if I took the derivative of cotangent of u, that's equal to negative cosecant squared of u times u prime. All right. So those are your 6 trigonometric functions, and that's how you would take the derivative of each of those. I wish there was a better way than saying just memorize it, but the truth is that's how you do it. You just have to memorize these derivatives and then make sure that you apply them. And really the best way of memorizing them is to do as many problems as you possibly can. I mean, I can only do so much with problem sets. I'll try to give you as much as I can, but if that's not enough, then seek out more problems on worksheets or anything like that. You can look for patterns here. Like a couple of patterns that I notice is that if it's obviously the sine and cosines, those are the easiest. Those are just going to be like the opposite of each other. So if it goes from sine, it goes to cosine. If it goes from cosine, it goes to sine. You'll notice that with the tangent, it's obviously going to be something squared, right? So tangent is just a secant squared and cotangent is cosecant squared. And the cosecant and secant, those are just kind of like themselves plus a little extension. So again, just look for little patterns like that. Another thing too is like if you originally started with cosine, cotangent, cosecant, those derivatives are going to be negative. If I think of more patterns, I'll probably just let you know at some point. But secant and tangent kind of always like tie in with each other. Cosecant and cotangent, again, those kind of tie in with each other. And I don't know, that's about it. You just kind of have to go on your own and sort of figure out what will help you best remember these derivatives. So let's kind of put a few of these into practice. I want to do A, D, F, and I. So to find the derivative of f of x, I'm going to go ahead and say that's f prime of x is equal to, well, we know that the derivative of sine should be cosine. So it's going to be cosine of 2x cubed times the derivative of the inside. So that's going to be 6x squared, right? And I like to put my variables first. So 6x squared cosine of 2x cubed. All right. And then for this one, the derivative of secant, you should remember, is secant tangent, right? Double check. Yep. Derivative of secant is going to be secant tangent times the derivative of u. So I wish I should have given more space for this, but whatever, I'll just do it. So this, y prime is equal to secant of u, so 5, times tangent of u, times the derivative of the inside. So I'll just say 3, right? So I could have moved the 3 right there to the front, but because I don't have that much space, I'll just kind of move on. All right, now this one, it's a little bit more complicated because now we have tangent to the 5th, right? So tangent raised to the power of 5 of 3t cubed plus 5t. So I know some of you have a hard time seeing, like, understanding what to do with this 5, but really just kind of ignore that for now and just pretend like this whole thing is raised to the 5th power, okay? They put it there because they don't want to get you confused and make you think that that inside the tangent is raised to the power of 5. They put it there so that you know that the whole thing is raised to the power of 5, right? So in a situation like this, it would make sense to just go ahead and do the chain rule we learned from earlier, where we get the power, we bring it to the front, so that's 5, rewrite the inside, tangent of 3t cubed plus 5t, subtract 1 from the exponent, and then multiply it by the derivative of just the inside. So if we didn't even have that 5th power, if we took the derivative of just that, well, derivative of tangent is secant squared, so it's going to be times secant squared of 3t cubed plus 5t, and then we still have to multiply it by the derivative of the inside of this, because again, if I were just taking the derivative of that, it would be secant squared of u times the derivative of u, so then that becomes 9t squared plus 5. So you can see how some of these derivative problems can get a little bit crazy. I highly regret making worksheets where the boxes are this small, but I mean, I think down here I gave you enough space, so that should be helpful. Same thing over here. If it's cotangent cubed of x to the 5th, well, let's kind of think of the whole thing as being cubed. And I'm going to bring the 3 up to the front, so that's 3. I should have said h prime of t, f prime of x. So f prime of x is equal to, so let's bring the 3 up to the front, 3 parentheses, leave the inside alone, cotangent of x to the 5th, and then all raised to the power of 2, times the derivative of the inside. So the derivative of the cotangent was, oh my god, it was negative cosecant, times negative cosecant of x to the 5th, and then times the derivative of the inside again, 5x to the 4th. All right, so I'm going to make this look a little bit better. So I have a negative and a 5x to the 4th and a 3, so I'll go ahead and combine those. That'll be negative 15x to the 4th. And then I'm going to rewrite this as cotangent, because again, the squared would usually be attached to the trig function, cotangent squared of x to the 5th, and then cosecant of x to the 5th. All right, so that becomes the derivative of that. And this is what I imagine it would look like on the multiple choice part, if it was a multiple choice answer choice. But yeah, like I said, you can see how some of these can get a little bit complicated. So really, the best way of getting good at these is just practice them as much as you can. So there you go. I went over a few examples. Here are some practice problems that I'll try to post the solutions to soon. And if you have any questions, just let me know. Feel free to ask. Take care.